In this next example, we're going to try to put all of the things together from section 4.5. Our goal is to find all the real zeros of the polynomial. Another problem that would do this would be to factor the polynomial completely. So let's start by pointing out that we could have up to 5 real zeros, since this is a fifth degree polynomial. And we want to decide whether or not we want to look for some positive zeros or negative zeros. So use Descartes' Rule of signs to decide what that's going to look like. So we're going to go positive to negative to positive to negative to positive to negative. What that tells us, we have 1, 2, 3, 4, 5. So we may have 5 positive zeros, or 3, or 1. Remember to reduce that by 2 each time. So there's definitely going to be at least one positive zero there. We can change the signs of all the odd powers and do Descartes' Rule of signs for the negative zeros. And it looks like all of those are negative. So there are 0 negative zeros. That's nice because now we don't have to bother with negative zeros. All of our zeros are going to be positive zeros. So what values should we check? We're going to use the P over Q, or the rational zeros theorem. So we need to look at the factors of P. And P is 36, so the factors of P are 1 times 36, 2 times 18, 3 times 12, 4 times 9, and last 6 times 6. And then the factors of Q, Q is the leading term, leading coefficient is just 1. So when we do P divided by Q, we'll take 1 over 1, 2 over 1, 3 over 1, 4 over 1, 6 over 1, 9 over 1, 12 over 1, and 18 over 1, 36 over 1. So those are just the same. 1, 2, 3, 4, 6, 9, 12, 18, and 36. We don't have to do plus or minus here, since we noted that there were no negative zeros from Descartes' Rule of signs. Well, at this point, we can start doing synthetic division to try to find out whether or not each of these are zeros. However, I'm going to cheat a little bit, and I'm going to use my calculator to graph in order to shorten our problem a little bit. If we type the graph in on our calculator, we get a sketch that looks like this. And what it looks like is that we're going to have a 0 at 1 and a 0 at 3. But what we know is that since we cross at 1, the multiplicity there is odd, and since we touch at 3, the multiplicity there is even. So I suspect that when we do synthetic division, we'll have 1 0 at 0, and then we'll have 2 zeros at 3. We'll just have to work it out and see how it goes. Let's start with 1. looking back at our original problem, we're taking a look at the coefficients and the powers. Notice that there are no missing terms, 5, 4, 3, 2, 1, and then a constant term. So we'll take our coefficients, and the coefficients were 1, -7, 19, -37, 60, and -36. Start by carrying down the 1. Then 1 times 1 is 1. -7 plus 1 is -6. 1 times a -6 is -6. 19 minus 6 is 13. Times 1 is 13. 37, -37 plus 13 is a -24. Times 1 is -24. 60 minus 24 is 36, and times 1 is 36, giving us a remainder of 0. That's good news. So what that means is that x equals 1 is a 0, or x minus 1 is a factor. Now, if x minus 1 is a factor, that means the rest of this can be multiplied by x minus 1. And if we read this from the 36 going that way, we've got 36 as our constant, a -24 with an x, a 13 with an x squared, -6 with x cubed, and 1 with x to the 4th. We don't really have to write those out again, but we are going to use those values for our next try. We decided that it would be a good idea to try 3 with multiplicity 2. So I'm going to go with 3, and I'm going to copy down that. This is called a depressed equation. That's some trivia for you. You don't need to know that name. 3 times 1 is 3. Minus 6 gives us -3. Times 3 is a -9. Plus 13 is 4. Times 3 is 12. Minus 24 is -12. Times 3 is -36. And we're left with another remainder of 0. Which means that x equals 3 is a 0, or x minus 3 is a factor. Now, we have another depressed equation, and notice that it's one term shorter than the previous equation. So we're going to do it again. I'm going to do 3 again since it looks like there's a multiplicity of 2 here. 1. 3 times 1 is 3. 3 minus 3 is 0. 3 times 0 is 0. 0 plus 4 is 4. 3 times 4 is 12. 12 minus 12 is 0, which means x equals 3 is a 0. So we have another x minus 3 as a factor. Let's take a look at what we have left. What's left, we have 4 as our constant term, 0 x's, and then 1 x squared. So we're left with an x squared plus 4. So at this point we can use our factoring techniques that we know, or we can try to solve this by setting it equal to 0, depending on what our goal is. since our goal was to look for all of the zeros, then I'm going to set this equal to 0 and try to find solutions. It looks like we're going to end up with plus or minus the square root of -4, which is plus or minus 2i. Well, those are not real zeros. So I can list all of the zeros that we've found. Going back, we found plus or minus 2i. We found 3 repeated, and we found 1. Okay, so that's one way that this question could be asked. The second way that this question could be asked was factor completely. So if we look back at the factors, here we see our factors. If x equals 1 is a 0, x minus 1 is a factor. So we can say 0 factor, 0 factor, and so on. All right, so if we list these out, it looks like to factor our equation, we've got an x minus 1, we've got an x minus 3 squared, and then depending on whether or not we want to factor with imaginary numbers or not, then we can either say, hey, we've got that left and write it as x squared plus 4, or we can break that down and write it as x plus 2i, x minus 2i. Where do we get this x plus 2i and x minus 2i? Well, that comes from here. And we've found all of the solutions. We've found zeros of 1 and 3, and then some complex solutions, or we've factored our polynomial completely. So that would be a great example of a test question. Maybe you should put a heart next to it.